topic, we want to delve deeper into the activation function. But hopefully for now, everything should be pretty clear how, you've got input values, you've got weights, you've got the synapses, you've got something, happens in the neuron, you've got a weighted sum, and then an activation function applied, and then that is passed down the line, and that is just repeated throughout the whole neural network on and on and on and on. Thousands, hundreds of thousands of times, depending on how many neurons you have, how many synapses you have in your neural network. So there we go.
So here you need to remember the single graph or single diagram. So how simple neuron works. So here initially we need to consider inputs. After that, applying weights. After that, weighted sum is nothing but output. We need to apply this output to the activation function. Based on this activation function, we will get output value. So here we have different activation functions. Those are step activation function, ReLU activation function, sigmoid activation function. In this session, we will discuss regarding those activation functions.
Hello and welcome back to the course on deep learning. All right, today we're talking about that it has some inputs values coming in, it's got some weights, then it adds up it calculates a weighted sum of those inputs, and then applies the activation function, and on step 3, it passes on the signal to the next neuron. And that's what we're talking about today. We're talking about the value that is going to be passed over, so we're talking about the activation function that's being applied. So what options do we have for the activation function? Well, we're going to look at 4 different types of activation functions that you could choose from. Of course, there are more different types of activation functions, but these are the predominant ones that you'll be hearing about and that we'll be using in this course. So here is the threshold function. This is what it looks like. So on the x-axis, you have the weighted sum of inputs. On the y-axis, you have just, the values from 0 to 1. And basically, the threshold function is very simple.
So it is the first kind of activation function. It is a threshold function, whereas it is not a suggestible function for most of the problems. So mostly we need to use this threshold function or sigmoid function in the case of classification problems. So here I'm not suggesting you to use this threshold function for any scenario. Why? Because here we have sharp peak. So here, if you want to apply this thing in any machine learning algorithm or any practical problem, we need to have smooth curve. Whereas coming to this case, we have sharp peak. So in these cases, what happens there? What will be the problem on this kind of cases? So in this case, if you apply some activation function on it, so let's assume if you are having probability of 0.1. So in case of 0.1 also, that point lies here. So on the x-axis, this point lies here. Whenever this point lies here, then also it becomes category 1 only. So here, if it is a category 0.2, then also it will predict output as 1 only. If it is a value of 0.5, then also it will predict category as 1 only. So here, in case of less probability values, also it is predicting as a category 1 only. So that's why here, I don't suggest you to use this threshold activation function. Coming to the formula for this threshold activation function, here it is a formula. So here, pi of x equals to 1 if x is positive. If x is positive, it will goes to 1. If x is negative, it will stay at 0 level only. So here, for the binary classification problem, if you want to use the threshold activation function, you can use. So here, it will be useful for binary classification problem only.
Function. Let's move on to something and 1 plus e to the power of minus x. Whereas,
so here it is the sigmoid function. Here, if you observe, here we don't have smooth curve. So here we don't have sharp peak. It is a smooth curve. For the classification problem, in place of threshold function, we can use this sigmoid activation function. And it is the formula for this sigmoid activation function. What is the formula? 1 by 1 plus e power minus x. So here, x is nothing but this entire portion. X is nothing but here, this entire portion is said as x in this scenario. And here it is the output. So it is also a function which is applicable for binary classification problem only. So here, whenever you want to use this threshold function at the output layer, whenever you want to use activation function before the output layer, then sigmoid function is the suggestible one. If it is a categorical data, then only it is a suggestible activation function.
In this case, of course, x is 0. It is 0.
And the next activation function is the ReLU activation function. So here rectifier, it will also said as rectifier linear unit function. So remember this thing, most of the cases in the hidden layers, we are using rectifier linear unit function. In most of the cases in the hidden layers, we are using this activation function. It is said as rectifier linear unit function. In shortcut, it will be said as ReLU activation function. The formula for this thing is max of x comma 0. And if your output is a continuous value, if your output is continuous value, on that cases also, we need to use this ReLU activation function only. So if your output is the categorical, then better to go with the sigmoid. If your output is a continuous value, then better to go with the ReLU activation function.
And then from there, it gradually progresses as the input value increases as well. And we'll see that throughout the course. We'll see that in other intuition tutorials, and we'll also see that how we use this function in the practical side of the course. And I will comment on this a bit more in a few slides from now. So just remember that a rectifier function is one of the most used functions in artificial neural networks. And finally, we've got one more function that you will probably hear about. It's the hyperbolic tangent function. It's very similar to the sigmoid function, but here the hyperbolic tangent function goes below 0. So the values go from 0 to 1, or approximate to 1, and go from 0 to -1 on the other side. And that can be useful in some applications. So we're not going to go into too much depth on each one of these functions. I just wanted to acquaint you with them so that you know what they look like and what they're called. If you'd like to get some additional reading, then check out this paper by Javier Glorot, called Deep Sparse Rectifier Neural Networks 2011 paper. And there you will find out exactly why the rectifier function is such a valuable function, why it's so popularly used. But nevertheless, for now, you don't really need to know all of those things. For now,
So for till now, remember the ReLU activation function. So advantage of ReLU activation function is, so to avoid vanishing gradient problem in deep learning, we are using this rectifier linear unit function inside the hidden layers. So that problem I will explain you after finishing all these tutorials. So here I will explain you this entire thing in the paint.
we just start applying the tutorial. Let's quickly the sigmoid activation function, which looks like this. We have the rectifier function, and we have the hyperbolic sink in. So variable is binary, so it's either 0 or 1. Which threshold function would you use? So out of the ones that we've discussed, we have the threshold function, the sigmoid function, the rectifier function, and we've got the hyperbolic tangent function. In their raw forms, which ones would you be able to use for a binary variable? Okay, so the answers here are, there's two options that we can approach this with. So number one is the threshold activation function, because we know that it's between 0 and 1, and it gives you a 0 under certain values, and then otherwise it gives you 1, so it only can give you 2 values. It fits perfectly, fits this requirement perfectly, and therefore you could just say y equals the threshold function of your weighted sum, and that's it. And in the second case, what you could use is the sigmoid activation function. It is actually also between 0 and base of y to have a rectifier activation function. So it would look something like that. We apply the rectifier activation function, and then from there, the signals would be passed on to the output layer, where the sigmoid activation function would be applied, and that would be our final output, and that could predict a probability, for instance.
So here for this reason will be there. So why we are using hidden, so ReLU activation function at the hidden layers. The reason is to avoid vanishing gradient descent problem. So I will explain you this thing while discussing regarding back propagation. Whenever we discuss the back propagation, there I will explain you why we are using ReLU only at the hidden layer.
This combination is going to be quite common, where in the hidden layers we apply the rectifier function, and then in the output layer we apply the sigmoid function. So there we go. Hope you enjoyed today.
So if your output is the continuous, so categorical value, then only sigmoid function is the preferable. So if it is a binary classification problem, then only sigmoid function is preferable. Whereas if it is a multiple classification problem, so if you have multiple categories here, in place of the sigmoid function, we need to use softmax function. So here softmax is a one more function which is applicable for this categorical data. If you have more than 2 categories, then better to go with softmax function. Whereas if you are having output like a continuous values, then better to go with a ReLU activation function only. In place of output also, if it is a continuous value, better to go with rectifier linear unit function only.
All right, exciting tutorial ahead. What? So we're going to look at a neural network that takes in some parameters about a property and values it. And the thing here, there's a small caveat for today's tutorial, and that is we're not actually going to train the network. So a very important part in neural networks is training them up. And we're going to look at that in the next tutorials in this section. For now, we're going to focus on the actual application. So we're going to work with a neural network that we're going to pretend is already trained up, and that will allow us to focus on the application side of things and not get bogged down in the training aspect. And then we'll cover off the training when we already know the end goal we're working toward. Sound good? All right, let's jump straight into it. So let's say we have some input parameters, right? So let's say we have 4 parameters about the property. We have area in squared feet, we have the number of bedrooms, the distance to the city in miles, the nearest city, and the age of the property. And all of those 4 are going to comprise our input layer. Now, of course, there are probably way more parameters that define the price of a property, but for simplicity's sake, we're going to look at just these 4. Now, in its very basic form, a neural network only has an input layer and an output layer, so no hidden layers. And our output layer is the price that we're predicting. So in this form, what these input variables would do is they would just be weighted up by the synapses, and then the output layer would be calculated, or basically the price would be calculated and we get a price. And for instance, the price could be calculated as simple as the weighted sum of all of the inputs. And again, here you could use pretty much any function. You could use what we're using now. We could use any of the activation functions we had previously. You could use a logistic regression. You could use a squared function. You could use pretty much anything here. But the point is that you get a certain output. And moreover, most of the machine learning algorithms that exist can be represented in this format. This is basically a diagrammatic representation of how you deal with the variable, right? By changing the weights, the formulas, you can accomplish quite a lot of the machine learning algorithms that we've talked about before, and put them into this form. And that just stands to show how powerful neural networks are, that even without the hidden layers, we already have a representation that works for most other machine learning algorithms. But in neural networks, what we do have is an extra advantage that gives us lots of flexibility and power, which is where that increase in accuracy comes from. And that power is the hidden layers. And there we go. That's our hidden layer. We've added it in. And now we're going to understand how that hidden layer gives us that extra power. And in fact, to do that, we're going to walk through an example. So as we agreed, this neural network has already been trained up. And now we're just going to plug in, we're going to imagine that we're plugging in a property, and we're going to walk step by step through how the neural network will deal with the input variables and calculate the hidden layer and then calculate the output layer. So let's go through this. It's going to be exciting. All right. We've got all 4 variables on the left. And we're going to first start with the top neuron on the hidden layer. Now, as we previously saw in the previous tutorials, all of the neurons from the input layer, they have synapses connecting it, each one of them, to the top neuron in the hidden layer. And those synapses have weights. Now, let's agree that some weights will have a non-zero value, some weights will have a 0 value, because basically not all inputs will be valid, or not all inputs will be important for every single neuron. Sometimes inputs will not be important. And here we can see two examples that x1 and x3, the area and the distance to the city in miles, are important for that neuron, whereas bedrooms and age are not. And let's think about this for a second. How would that be the case? Why would a certain neuron be linked to the area and the distance? What could that mean? Well, that could mean that normally, the further away you get from the city, the cheaper real estate becomes, and therefore the space in square feet of properties becomes larger, right? So for the same price, you can get a larger property the further away you go from the city. That's normal, right? That makes sense. And probably what this neuron is doing is it is looking specifically, it's like a sniper. It's looking for area properties which are not so far from the city, but have a large area. So for their distance from the city, they have an unfair square foot area, right? So something that's abnormal, it's higher than average. So they're quite close to the city, but they're still large, as opposed to the other ones at the same distance. And so that neuron, again, we're speculating here, but that neuron might be picking out later.
Simple thing here. So let us assume here it is the first person, it is the second person, it is the third person. So coming to one person perspective, what happens? He will consider few parameters only. Like that coming to another person, so to purchase the house, some person might consider these rooms. So these constraints like a bedroom as well as the age of the building. Coming to the second person, he will consider like bedroom, distance as well as age of the building. So like that. So whatever the parameter he is considering, we need to activate those functions. We need to assign weights to those things. Whereas whatever the things you are not considering, we need not to assign weights to that thing.
They're picking out those specific properties, and it will activate, and hence the activation function. So this the thinking of this neuron. How is this neuron thinking? Why is it picking these three parameters? What could it be? What could have found in the data, right? So we've already established this is a trained up data set. The training has happened a long time ago, maybe like a day ago, or somebody's already trained up this data. So now we're just applying, and we know that this neuron, through all of the thousands of examples of properties, has found out that the area plus the bedrooms plus the age, combination of those parameters, is important. Why could that be the case? Well, for instance, maybe in that specific city, in those suburbs that this neural network has been trained up in, perhaps there's a lot of families with kids, with 2 or more children, who are looking for large properties with lots of bedrooms, but which are new, right? Which are not old properties, because maybe in that area, most of the properties are kind of like big properties are usually old, but there's lots of modern families, and maybe has been a socio-demographic shift, and or maybe there's been like a lot of some growth in terms of employment and jobs for the younger side of population. Maybe just the population demographics have changed, and now younger couples or younger families are looking for properties, but they prefer newer properties. So they want the age of the property to be lower. And hence, from the training that this neural network has undergone, it knows that when there's a property with a large area and with lots of bedrooms, with at least three bedrooms for the parents, for the first child, for the second child, for at least 3 bedrooms, maybe a guest room, when a new property with a high area and lots of bedrooms, that is valued. That in that market, that is valuable. So that neuron has picked that up. It knows that, okay, so this is what I'm going to be looking for. I don't care about the distance to the city in miles, wherever it is, as long as it has high area, lots of bedrooms. As soon as that criteria is met, the neuron fires up. And the combination of these 3 parameters, and this is where the power of the neural network is coming from, because it combines these 3 parameters into a brand new parameter, into a brand new attribute that helps with the evaluation, helps with the valuation of the property. It combines them into a new attribute, and therefore it's more precise. So there we go. That's how that neuron works. And let's look at another one. Let's look at the very bottom one. For instance, this neuron could even have picked up just one parameter. It could have just picked up age and not any of the other ones. And how could that be the case? Well, this is a classic example of when age could mean, like, as we all know, the older property is usually it's less valuable because it's worn out. Probably the building is old. Probably things are falling apart. More maintenance is required. So the price drops in terms of the price of the real estate. Whereas a brand new building, it would be more expensive because it's brand new. But perhaps if a property is over a certain age, that could indicate that it's a historic property. For instance, if a property is under 100 years old, then the older it is, the less valuable it is. But as soon as it jumps over 100 years old, all of a sudden it becomes a historic property because this is a property where people used to live hundreds of years ago. It tells a story. It's got all this history behind it, and some people like that. Some people value that. In fact, quite a lot of people would like that and would be proud to live in a property, and especially in the higher socioeconomic classes, they would show off to their friends or things like that. And therefore, properties that are over 100 years old could be deemed as historic, and therefore this neuron, as soon as it sees a property over 100 years old, it'll fire up and contribute to the overall price. And otherwise, if it's under 100 years old, then it won't even work. And this is a good example of the rectifier function being applied. So here you've got like a zero until a certain point, and then let's say 100 years old, and then after 100 years old, the older it gets, the higher the value, the higher the contribution of this neuron to the overall price. And it's just a wonderful example of very simple example of this rectifier function in action. So there we go. That could be this neuron. And moreover, the neural network could have even picked up things that we wouldn't have thought of ourselves, right? For instance, bedrooms plus distance to the city. Maybe that in combination somehow contributes to the price. Maybe it's not as strong as the other neurons and it contributes, but it still contributes. Or maybe it detracts from the price. That could also be the case. Or other things like that. And maybe a neuron picked up a combination of all four of these parameters. And as you can see, that these neurons, this whole hidden layer situation allows you to increase the flexibility of your neural network and allows you to allows the neural network to look for very specific things, and then in combination, that's where the power comes from. It's like that example of the ants, right? Like an ant by itself cannot build an anthill, but when you have like 1,000 or 100,000 ants, they can build an anthill together, right? And that's the situation here. Each one of these neurons by itself cannot predict the price, but together they have superpowers and they predict the price, and they can do quite an accurate job if trained properly, if set up properly. And that's what this whole course is about, in understanding how to utilize them. There we go. So that is a step-by-step example and walkthrough of how neural networks actually work. I hope you enjoyed today's tutorial, and I can't wait to see you next time. Until then, enjoy deep learning. Hello and welcome back to the course on deep learning. Now that we've seen new outcomes, networks where you create a facility for the program to be able to understand what it needs to do on its own. So you basically create this neural network where you provided inputs, you tell it what you want as outputs, and then you let it figure everything out on its own. Two fundamentally different approaches. And that is something to keep in mind as we go through these tutorials. Our goal is to create this network which then learns on its own. We're going to avoid trying to put in the rules. And a good example that I can give you right now is, this will come further in the course, but it's just a very visual example. For instance, how do you distinguish between a dog and a cat? For on the left side, on the approach that's depicted on the left, you would program things in like the cat's ears have to be like this, look out for whiskers, look out for this type of nose, look out for this type of shape of face, look out for these colors. You describe all of these things, and you'd have conditions like if the ears are pointy, then cat, if the ears are sloping down, then possibly dog, and so on. On the other hand, for a neural network, you just code the neural network, so you code the architecture, and then you point the neural network at a folder with all these cats and dogs, with images of cats and dogs, which are already categorized, and you tell it, okay, I've got some images of cats and dogs. Go and learn what a cat is. Go and learn what a dog is. And the neural network will on its own understand everything it needs to understand. And then further down, once it's trained up, when you give it a new image of a cat or a dog, it'll be able to understand what it was. So there they are. Those are the two fundamentally different approaches. And today we're going to slowly start getting into how that second approach works. All right, so let's get straight to it. Here we have a very basic neural network with a one layer. This is called a single layer feed-forward neural network, and it is also called a perceptron. Now, before we proceed, one thing that we do need to adjust is that output value. Right now, you can see that it's just a Y. We need to put a Y hat in there, and the reason for that is usually Y stands for the actual value, and that's what we're going to be using. So Y is going to be the actual value, which we see in reality. Output value is the predicted value by the algorithm, by the neural network. Y hat is the
So here in this he used the term called perceptron. Perceptron is nothing but fundamental unit of neural network is called as perceptron. So here it is a single neuron, that's why he is saying this neuron as an perceptron. Perceptron is nothing but it is a fundamental unit of any neural network.
output value. Basically, that's the denomination for the output value. And the perceptron was first invented in 1957 by Frank Rosenblatt. And his whole idea was to create something that can actually learn and adjust itself. And this is what we're going to be looking at now. So we've got our perceptron. Let's see how a perceptron learns. So let's say we have some input values that have been supplied to the perceptron or basically to our neural network. Then the activation function is applied. We have an output. And now we're going to plot the output on a chart. So there it is, our output Y hat. Now, what we need to do is, in order to be able to learn, we need to compare the output value to the actual value that we want the neural network to get, right? And that is the value Y. And so if we plot it here, you'll see that there's a bit of a difference. Now we're going to calculate a function called the cost function. It's calculated as 1/2 of the difference, the squared difference between the actual value and the output value. Now there are many ways you can come up with a cost function. There are many different.
So here it is called as feed forward propagation. So here we are moving from input to output. The process, the path which we are moving from starting to end is called as feed forward propagation. So here in this feed forward propagation, we are getting the cost function. So here our main aim is to adjust the weights in such a way that we need to reduce this cost. That means we need to make this cost as minimum as possible. So for that purpose, what we need to do? Here again we need to perform back propagation. So here it is our predicted outcome, whereas here it is actual outcome. So whereas we need to minimize this thing. We need to maximize this thing in this case. So for that purpose, we need to update the weights. That is called as back propagation.
Cost functions that you can use. This is probably the most commonly used cost function, and basically the only thing that we have.
So here it is called as back propagation. So here initially we are assuming some random weights. Based on those random weights, we got some output. So here it is our predicted output. So if you observe the difference between both the things, we got this thing as a cost function. Whereas we try to reduce this cost function. So here we need to make this cost function as minimum as possible. So for that purpose, we are moving in backward direction. Here we are moving in backward direction and we are updating the cost function. So the weight updation formula for the cost function will be, so here I will write down here that formula. So here formula will be, so W new, no problem. So I will explain you this formula in the next session. Don't worry about that thing. So how to take this weight, so how algorithm will take this random weights and how to update those weights. So weight updation formula, I will explain you that thing, and what are the problems with those formulas also I will explain you in the next tutorial.
Control of in this very simple neural network are the weights W1, W2, all the way to Wm. And our goal is to minimize the cost function, so all we can do is update the weight. So we update the weights. tweak them a little bit, and how exactly we'll find out further down. But for now, we agree that we update the weights, and then we continue. So, but here I've put up this screenshot of the data just to make one point very clear, that right now, throughout this whole experiment, everything we're doing right now, we're dealing with just the one row. So we have a data set of one row where we have, for instance, we're dealing with how long you study, like the variable that we're predicting is what results you're going to get on an exam, and the independent variables that we have is how many hours did you study for, how many hours did you sleep, and what did you get on the quiz in the mid-semester. So in the middle of the semester there's a quiz, what percentage did you get there? So based on those variables, we're trying to predict what score you'll get for the exam. And in exam, the 90 weights get adjusted. So as you can see, let's do this again. We're going to feed the values. Again, the point here is that we're feeding in these same values. So we only have one row. We're training on one row. This is because this is changing. Let's have a name, adjusted the weights. We feed in the information.
Eventually, we need to assume some random weights. Based on that random weights, we need to compare our predicted output with the test outputs. So after that, if we won't get the proper cost function, so if it is not a minimum cost function, again we need to move from output to the input. So by moving from backward propagation, we need to update this random weight. We need to modify this weights. Again, we need to compare this input and output. So iteratively, we need to move from feed forward neural network. So in the forward direction, as well as we need to move in the backward direction. Wherever we got the optimum weight, wherever we got the optimum or minimum cost function, there we need to stop this process.
And there we go. So now this time the y hat is equal to y, cost function 0. Usually you won't get cost function equal to 0, but this is a very simple example. So hopefully all that made sense. Every time we feed in exactly that same row, because just in this case we're just dealing with that one row, into our neural network, where then the values get multiplied by the weights, the activation function is applied, we get y hat is compared to y, then we see how the cost function is changed, feed that information back into the neural network, and then just adjust the weights again. And then we repeat the same process again with the same exact row, and we're trying to minimize that cost function. So up until now, we've been dealing with just that one row. Let's see what happens when you have multiple rows. So here's the full data set. We have 8 rows of how many hours you slept, or maybe these are different students they taking the same exam, how many other hours they studied, how many hours they slept before the exam, what they get on the quiz, and their final result on the test. And as you can see here on the left, I've got 8 of these perceptrons. Actually, they are all the same perceptron, so this is also important to understand. I just multiplied it, or like duplicated 8 times, just so that we can conceptually understand. But the important thing here, it's the same neural network. We're going to be feeding these into the one same neural network. So let's get started. So one epoch, as you'll hear Hadlan mentioning, one epoch is when we go through our whole data set and we train our neural network on all of these rows. So let's get started. So there's our first row, and there's y hat for the first row. There's the second row, there's y hat for the second row. So again, it's being fed into the same neural network every time. I've just copied them several times so we can visually see how this is happening. Then again, it's happening again. That's third row, fourth row. There's our y hat for the fourth row, and so on. Basically, then we get the same values for the remaining 4 rows as well. So every time we just feed in a row into our neural network, we get a value. Then we compare to the actual values. So there are the actual values. So for every single row, we have an actual value. And now, based on all of these differences between y hat and y, we can calculate the cost function, which is the sum of all of those squared differences between y hat and y, and all of that is halved. And there's our cost function. And basically now what we do after we have the full cost function, we go back and we update the weights. We update W1, W2, W3. And the important thing to remember here is that all of these perceptrons, all of these neural networks is actually one neural network. So there's not 8 of them, there's just one. And when we update the weights, we're going to update the weights in that one neural network. So basically the weights are going to be the same for all of the rows. So it's not the case that every row has its own weights. No, all of the rows share the weights. And so that's why we looked at the cost function, which is the sum of the squared differences. And then we updated the weights. And now from here, that was just one iteration. Next, we're going to run this whole thing again. We're going to feed every single row into the neural network, find out our cost function, and do this whole process again. So just as we saw previously, where we had just one row and we were doing everything again and again, again, same thing here, but now we're going to be doing it with 8 rows or 800 rows or 8,000 rows, however many rows you have in your data set. You do this process and then you calculate the cost function. And the goal here is to minimize the cost function and to get, as soon as you've found the minimum of the cost function, that is your final neural network. That means your weights have been adjusted and you have found the optimal weights for this data set that you're training on, and you're ready to proceed to the testing phase or to the application phase. And this whole process is called backpropagation. So some additional reading that you might want to do for the cost function. And I know we just talked about one, and there are many different ones. A good article is located on Cross-Validated. It's called A List of Cost Functions Used in Neural Networks Alongside Applications. So the URL is there, but you can just Google for that exact search term or search phrase, and this one will be the first one that pops up. It's actually got some good examples and application or use cases for different cost functions. So if you're interested to learn more about cost functions, check out this article. And on that note, I hope you enjoyed today's tutorial. I look forward to seeing you next time. Until then, enjoy deep learning.
So I will forward you the one more video link. So join on the session. So on that session, I will explain you everything. So how will be this weight updation formula will be, as well as after that I will explain you what is gradient descent and what are the different cost optimization methods, and how these weights will be randomly assumed by your algorithm. So I will explain you that kind of stuff in this next session. So here it is a very important session. Connect to that session.